Hi everyone. So in this video we're going to continue where the previous two videos left off. So in the previous video we looked at descriptive statistics and visualizing those and computing those, and now we're going to look at testing an assumption which is quite important to a number of statistical models. And that is to check whether data are normally distributed or not. So, particularly for parametric tests, it might be important to when making kind of decisions on whether you're going to use parametric tests or non-parametric tests, it might be important to know whether original data or residuals are normally distributed equally. You might have a population of which you believe to be normally distributed data, and when you sample that you might want to check if the sample of data that you've collected is normally distributed similar to the population itself. So normal distribution is sort of well, it is the distribution of your data. It's not, if it's normally distributed, it's not skewed in any particular direction, and it doesn't have a high level of kurtosis. So what it looks like, and to show you what it looks like, I will just kind of simulate some normally distributed data. So I'll call it normal data, and what I want to do, and I'm going to write a line of code, and I'm going to write a line of code to create a series of values first. So if you see up in my environment, there's values, which is that Irish summary table, but then there are there's data which comes above it. I'll create it just as a series of values first, and to create normally distributed data, you can use the ORNorm function. So ORNorm, and if you see there, it's an n, so a total sample size, a mean, and a standard deviation. So I'll do n equals 100 or 10 for the moment. I'll increase that in a second. I'll give it a mean value of 100 and a standard deviation of 15. And if I run this, you'll see now that the values is going to create. So we have a series of 10 numbers called normal data, and I'll take a look at what those numbers ended up being. And here are the 10 numbers. I should say, if I rerun it, it ends up being a different set of 10 numbers. And I can repeat this code multiple times, and it will continuously give me different sets of 10 numbers. So something that's important to do for reproducibility is this idea of setting a seed number. So if I set the seed number 4237, it's a integer that kind of drives the random number generator for RStudio. And now if I run it, I first set the seed, and then I create my random data. And you'll see if I keep now doing it, because my seed number is set, it is the same. So it's reproducible. And it's really important to have that set seed in whenever you're using sort of, whenever you're writing code which involves some form of randomness. This gives me a list of values, a series of values, 10 values, which are driven by a normal distribution and of 10, but 10 values is not really going to work for us, and I'll show you why. So I'm going to create a density curve of this, and I would use ggplot to do so. So I'll do ggplot with data equal normal data, and this isn't going to work. It's not going to work because my normal data isn't data. It's a series of, it isn't a data set. It's a series of values. And you'll see when I run it, data, the data that I'm specifying must be a data frame. So I'll create it as a data frame, and to do so it is literally as data frame. And I'll put all of this into brackets. So now when I run it, instead of normal data being a series of values, it's instead going to be as a data frame. So if I run this, it's no longer values. Normal data is a data frame. It's 10 observations, and you can see the code that was produced, and here they are. Now they're the exact same values as when they were a series of numbers, but now it's in a data frame, so I can use this code. This has nothing to it, so that was just creating the plot. Instead, I want to create a density plot. So I'll go to AES, setting mappings, x equals, and I'm going to run into a slight problem. I need the name of this column to be my x variable, and if I open normal data, it's relatively long. It's norm, it's that whole amount of code, and I don't necessarily want that to be the case. So instead, I'm going to change, and there's only one column name, so column names of normal data, there's only one, so it's a relatively simple piece of code. I will call it data points. If I run this line of code, within normal data, it's changed my variable to data points instead. Much easier to work with, so x equals data points in this plot. If I run that, you can see data points, and it's going to show them there. And I want this to be a density plot, so I'll use geom density. And can't add geom. I did forget the parentheses. And there's our density plot. It's not great, but that's because there's only 10 values. But what if there were 100 values? So I've just increased my n. I'll run the whole thing again. Slightly more normal looking. I'll add another magnitude bigger by 1,000. Getting closer. And rather than going through, I'll go to 1,000,000. And it's slowly but surely getting closer to a normally distributed, I've been changing the mean. My apologies. On the last two, I was wondering why it wasn't changing. I'll do 10,000 instead. Now it's starting to, that looks more appropriate. It's getting closer to a normally distributed curve. And I'll go the whole way to 1,000,000. I could go more. And now we're getting very close. And this is actually the central limit theorem. Large numbers, randomly distributed, tend to follow a normally distributed shape. And you can see it's quite even. 100 is our mean, and our standard deviation is 15, and it's pretty symmetrical either side. It's not too flat, it's not too pointy, peakness or tailedness or kurtosis essentially, and it's normally distributed. Skewness would be if we had, so roughly 50% of our data is lying either side of the mean in this case. Skewness would be if that curve was to have more data on one side of the mean than the other. Kurtosis would be to do with the relationship between the tails and the mean, and whether the shape was more flatter. It can be highly skewed or positive skewed, or positive kurtosis or negative kurtosis, and that kind of influences if it's more flat or more peaked. And it's a shape, but this is a normal distribution curve here of 1,000,000 data points with a mean of 100 and a standard deviation of 15. If we want to check, so what we want to do is check if our own data was normally distributed, and there are three kind of approaches. There's the checking for skewness and kurtosis. There is the visual approach, so we can use a density curve just like this and see if it resembles this curve. And we can do that with histograms, density plots like I've just shown you. And there's also a QQ plot, which I'll show you as well. And then the third approach is the statistical approach, so the Shapiro-Wilk test, for example, or the Anderson-Darling test. Could be the type of test that you want to use. So we'll do this with our own data. So we'll just leave a note. So checking normality of iris data. I'm going to press enter a few times just to drop some lines. And the first thing is, let's see, skewness and kurtosis. There is some references that would suggest that plus or minus 2 are acceptable limits. And if you recall earlier in the previous video, we looked at we created this iris descriptives table. So iris descriptives, we can check skewness and kurtosis. And if I do that, you should see the skewness here and kurtosis values. Sorry, I should make that wider to make it more visible. Iris descriptives, run that line of code. And here we can see, for example, skewness column, where my cursor is, and kurtosis column for each of the variables, for each of the variables for each of the species of iris. We also earlier we created the different. We created, for example, Setosa data. So if I attach the Setosa data for a moment, and so we've attached that. I could just check skewness for that. And I hope it's in the correct package. But let's say, so we can see Setosa, sepal length is a variable. Let's hope this works. Could not find the function skewness. I'm trying to remember what package the skewness one is in. I think, yeah, I have a package installed which I believe is called Performance Analytics. So maybe Performance Analytics. I think this will, if I run this, I'll load the package and try this again. Ah, it did. It was that package. So the Setosa sepal length skewness is 0.11, we can see from our descriptives table, but also I have skewness here as 0.116, so slightly, so it should be 0.12, I suppose, up above. And we can also check the kurtosis of it as well. Kurtosis, yeah, from there is also kurtosis. I'm not really sure how that one, how the one works in the site package, but I can use it from Performance Analytics, sepal length, and I can check its kurtosis value as well. So I could, for example, do this for all of the different variables within the Setosa data. I could attach to my different data sets that I created earlier, versicolor data or Virginica data, and do them that way. And that's a relatively straightforward way to check skewness and kurtosis of different variables. And that's one of the approaches that you can take. And as I said, there's citations out there that would suggest plus or minus 2 are acceptable limits in making a determination that something is normally distributed. The next approach would be the graphical approach. And I'll just kind of stick with the iris data set again. as a whole. So what options do we have? We've got a box plot. So iris box plot, for example. I'll make it in ggplot as before. So data equals iris, and our x-axis will be our species, and we'll stick with the sepal length variable. You may want to use a different variable. Y equals sepal length. I'm going to just move this in for a moment. And a box plot. So very simple, and I should also then take a look at it afterwards. Simple box plot, and what we're looking for here is sort of the kind of, we're almost imagining this top-down view of it, where here's your mean and it's moving towards the tails. Here you can kind of see it's more skewed than here. It looks more symmetrical around the median value. So that might suggest that for the setosa variable, sepal length is likely to be more closer to a normal distribution than, for example, the virginica species. We can see that in another way as well. For example, that John density plot. So iris density. We keep all of this the same, except at the end, rather than calling it a John box plot, we'll set up a John density plot and call it iris, or it is called iris density. So to view it, oh, I have not done that correctly. Iris density along my x-axis should be sepal length, and if I remember this, if I'm doing this correctly, this is going to not work out the way I want it to. It's going to work out like this, and the reason that it's working out like this is because I haven't differentiated that there are different species, so it probably wouldn't make sense for it to be normally distributed. So what I do in this circumstance is I want to differentiate the different species, and you differentiate them in ggplot by using either fill or color. Fill being the kind of fill inside, and color being the outline. I'll show you the difference. So fill by species, and now you can see the difference. Make it a bit more transparent, so you can see the difference between them. And that setosa one looks to be kind of more symmetrical than, for example, virginica. So it's another way of viewing the iris box plot, where this looks more symmetrical and this looks more skewed in that sense. And if we take a look what we mean by skewness and kurtosis here, if you were to imagine a vertical line through this may not be its mean, but its mean is probably somewhere over here. There's more data on one side of the mean than the other, and that would suggest it's either positively or negatively skewed. It's positively skewed, for example, in this circumstance where you've got more data on the positive side of the mean, and negatively skewed if there's more data on the negative side. And this also shows you a difference between kurtosis as well. Here you've got much more of a peak, and here you have more flatter curves. So if I was to check in the sepal length variable for skewness and kurtosis between setosa and virginica, which I can do from up here. So I'll do it with setosa, and I will also do it then with virginica. virginica and just take a look at the difference. So attach setosa, and we'll look at attach setosa, and I'll just do the kurtosis, and then attach virginica and also kurtosis. So you can see the difference. It's much closer to 0, the kurtosis for virginica, which is this one here, but it's much more negative because it's more peaked or has shorter tails in the setosa one. So there's your kurtosis difference. This is more of a negative value, this is more of a positive value. Other ways, I'll keep it there. Other ways that we can do it are, we have the QQ plot. So the QQ plot, there's also histograms, but I'm not going to go into histograms. I'll just show the QQ plot because it's a bit different. QQ plot will be iris QQ. Again, it's going to be GG plot as before, with our data equal to iris. This time, however, I was meant to show you the difference between fill and color. So instead of fill, I'll change this to color, so you can see the difference. What color did was the outline. Fill did the fill, color is the outline. I think fill is certainly the nicer option, at least in this case. But QQ plot is slightly different. So QQ plot is going to present a kind of theoretical line. So and it doesn't work with x and y axes. So yes. Instead, it works with your sample. And our sample in this case is the variable that we are going with. So we've got sepal length, and it's line, so we're not able to fill it in. We will do color, and color by the different species, species, and it'll be John plus John underscore QQ. I'm going to be putting into the QQ and the QQ line, but I'll just show you the difference between them first of all. Iris QQ. So what it's given us are these kind of sets of data, and the QQ plot itself put in the dots, but we want the QQ line as well. QQ line, and what this is going to put us is these lines which the data points would align with if the data was perfectly normally distributed. And here are those lines. The color is just used to differentiate the species. So the closer the data points fall along the line, the closer it is to be normally distributed. So there's 3 ways that we can graphically determine normal distribution. There's a density curve, there's box plots, and there's a QQ line. And then the final way is the statistical approach. So statistical approach, and we're going to look at 2 statistics. We're going to do the Shapiro-Wilk test, and we're going to do the Anderson-Darling test. Now the Shapiro-Wilk test comes from the R statics package, and as you become more familiar with the software, you start to learn what packages you need. So a Shapiro-Wilk test, what we're doing is testing a statistical significance test to see whether our data is normally distributed or not. Again, I'm going to attach the iris data set. I just do this because I previously attached the other data sets, and it's relatively straightforward. It is going to be Shapiro underscore test, and I like this one because it's pipe friendly, which I'll show either later on in this video or in a future video what I mean by that. as opposed to the Shapiro test, which isn't pipe friendly. And I'm going to stick with my same data, sepal length variable, and run this. The outcome, I'm just going to clear this so when I run it you can see clearly. Here we go. It's attached to the data set. It's run the test, and within the whole iris data set, the sepal length value, we have a test statistic and a p-value, and how we interpret this is if the p-value is less than 0.05, we conclude that we're rejecting the null hypothesis and the data is statistically significantly different to a normal distribution. So all of sepal length, the data for the whole iris data set is statistically different from normal distribution. This, however, is of course, excuse me, this, however, is of course the entire iris data set. So instead, what I might choose to do, and this is why it's important to use that pipe-friendly one. So if I take the iris data set, and this pipe can be interpreted as and then. So take the iris data set, and then that's what that percentage symbol, greater than symbol, percentage symbol can be kind of read as is, and then I want to group by, again from or statics, I want to group by species, and then if I go and then again, and I just do the Shapiro test as before, being careful to use only the underscore and for sepal length. Now what I'm going to do is take the iris data set, take all the different species and check and run the Shapiro test for them, and here none of them are less than 0.05, so we conclude that none of these are statistically different than normal distribution, which is different. When it was all a whole, we said it was, we inferred that it was statistically different to normal, and now because we're separating them, we're saying they're not. So you could use this on top of the QQ plot, on top of the on top of the graphical package and the skewness and kurtosis values. And of course you could do that for the entire data set. The final one, and just to show you one last approach, would be the Anderson-Darling test, and that comes from the NOR test package. I had to look over to my notes there and look that one up. The Anderson-Darling test is particularly useful in OR because the Shapiro-Wilk test is limited to data sets with 5,000 cases, but the Anderson-Darling test isn't. And it's used fairly similarly. It's ad.test. You can see from that. I'll attach iris beforehand and do sepal length one last time, and we interpret this the same way. This is less than 0. It's obviously a different test than Shapiro-Wilk, but it's less than 0.5, so we conclude it's statistically different than normal. This one can't be the piped though, which is what happened above. So instead, what you would have to do if you wanted to look at the different data sets, use the ones that we created earlier. If I do attach Setosa data first and then do the Anderson-Darling test for sepal length, we can check this one on its own, and here it's not less than 0.05, so we conclude that it is not statistically different than normal. There is, I suppose, one caveat to this. I said, this looks like it could be quite manual. What you could do is to do it this way. Rather than attaching the data the whole time, you could do your data set and then your variable. So you don't have to keep attaching. You can see there it's the same as the top and the bottom, data set, $, and then choose your variable rather than attach. But those are three methods to determine whether your data is or is not normally distributed, and they're probably best used as a collective, and it's generally good practice to visualize your data first.